Welcome to today's webinar, Exploring Advancements in Open Source Defined Architecture for PNT, brought to you by GPS World Magazine and our sponsor of the event, Aurelia. At the intersection of critical infrastructure and national defense, Aurelia Solutions govern and protect the time and location integrity of systems that shape the world. With over 40 years of experience and a growing portfolio of innovative positioning, navigation, timing, and GNSS simulation solutions, Aurelia's customer-first culture pushes the boundaries of quality, performance, and service. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it into the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and technical support specialist Marie Emmerich or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the right-hand side of your console. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see in the bottom left corner of your screen. I am Mackenzie Shoemaker from North Coast Media, Content Marketing Project Manager for GPS World, and I will be the moderator for today's event. Before we get started, I wanted to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. Now I'd like to introduce you to today's presenters. Today we will be hearing from John Fisher, VP Advanced R&D at Aurelia. John has been part of Aurelia for more than 15 years. He works with global navigation satellite systems, wireless positioning, navigation, and timing, as well as specialized systems for its customers. We will also be hearing from Lisa Perdue, Product Line Director, GNSS Simulation at Aurelia. Lisa is a world-leading expert in testing critical GPS and GNSS systems. She has trained hundreds of engineers and technicians who are responsible for high reliability positioning, navigation, and timing applications. We will also be hearing from Zahid Buyan, Research Professor at the Department of Navigation and Positioning at the Finnish Geospatial Research Institute. Zahid's main research interests include multi-GNSS receiver development, PNT robustness and resilience, seamless timing, seamless positioning, etc. He is actively involved in teaching GNSS-related courses in Finnish universities and other training schools. Before I hand the presentation over to John, we will be doing our first poll. So for our first poll, my apologies, we are asking, are you planning on using a GNSS SDR in your designs? We will give you about 30 seconds to answer. The options are no, considering use, planning to use, already using. At this time, you may enter your questions.
Mackenzie, while they're answering, just to be clear, an SDR, we're talking about a software-defined radio, and that's what we're going to be at least leading in this discussion with, is talking about what a software-defined radio is. And so I wanted to see if any of you folks are using that or considering it in your designs. That might be why you're here.
Okay, we'll allow for about 15 more seconds. Okay. Interesting. A lot of you are considering using it. All right, John, go ahead and take it away.
Great, thank you, Mackenzie. So as I said, I guess I'll start out with to introduce this session. Oops, let me go to the first screen. Is there? Okay. We'll start out with, of course, based on that poll, a number of you already maybe know what a software-defined radio is, but just so that we're all on the same page, I'll go over this, just kind of a general architecture. Of course, not all radios look this way, SDRs look this way, but in general, they follow this pattern. So I'm going to start at the top left-hand corner on the receive side. As we say, we start with a receive antenna and we amplify the signal, especially in GNSS. We're dealing with a very weak signal, so we go to amplify it with a low noise amplifier. We then drive that into a analog to digital conversion, which gets us right into the digital domain here, and that's where the real power happens of a open source software defined radio. You go from the first step typically is from the time domain, maybe into a frequency domain, down into where your information bandwidth is, do whatever digital filtering you need to do, then demodulate the signal, and you have your received data that you can then work with. On the transmit side, can we talk about a radio, or more precisely a transceiver? So there's both receives and transmits. So on a transmit side, you have data which you modulate, maybe also do some filtering, convert, then we call upconvert to into the carrier time domain, which you then take those digital values, probably typically digital I and Q values, which you then digital to analog conversion and into a power amp to amplify and then transmit out into space. I've skipped over the optional RF conversion portion of it here, but this is where, depending on what your A to Ds, D-Days are capable of, sometimes you can't go directly from your carrier frequencies right down to right to the digital domain. So you can do a heterodyne step to convert that and get it into a usable frequency. But at the kind of things, again, we're talking about GNSS receivers, and most modern SDRs now are capable of operating at gigahertz level, at least in this 1 to 2 gigahertz level, which is where L-band, which is where most of the GNSS frequencies are. So what is different? What's created this like revolution in SDRs? Because the idea has been around for a long time, but really the revolution is I would say is the RF ICs, the RF integrated circuits that have enabled LNAs or even power amplifiers. The gallium nitride power amplifiers of really making these things take off. As I mentioned, the A to Ds and the D to As, working at these at least L-band frequencies, and then the real power in digital signal processing. And I'll go into that a little deeper here in a moment. But the first thing is, and hopefully, I think a number of you who answered the poll probably have a good opinion on this. And if you were to ask me, should you use an open source receiver? Most of the time, the answer I give people is no. I say, why would you build your own receiver when there's been billions of dollars invested in receiver design? And these new receivers now, the mainstream ones, they're low cost, but yet very powerful. They're multi-constellation, multi-frequency. You're getting sub-meter accuracy and positioning, nanosecond accuracy and timing. They're doing all kinds of things of multipath mitigation and interference rejection and spoofing detection. So why would you do? There's, as shown here, there's millions of units field. So why would you do it? Well, so don't leave the webinar. I'm not trying to discourage you there. There is one good. Let's see if you can think of one good reason. Is if maybe you have a specific research topic you're doing or some very unique application. So and maybe that's what you folks, and maybe in our question and answer period we can hear more from you folks. But the so yes, and in fact, I use here an example. This is something we at Aurelia did about 10 years ago, and I kind of wish that the whole open source GNSS receiver was available 10 years ago. I want to tell Zaid that I wish his stuff was available then, because we were trying to do something like this. In this example, as you may know, these RTK receivers are capable of centimeter level positioning accuracy, and they do this through a differential signal reception, doing we call a double difference of by differencing, you can get a lot of the common mode errors out and reduce it. One of the common mode errors you get out is the clocking errors, and so we'd come up with this idea. Well, we can recover the clock if we get it back in, and we do all this stuff. But without a regular GNSS receiver can't do that. You couldn't do that with an RTK off-the-shelf receiver, and so there's real power, and you can go in there and do your own things there. So that's, I would say that's a good reason to do your own receiver. The next question, and now, so let's go back to the digital signal processing part. I was asked this question a few years ago of, okay, for my digital signal processing, should I use a FPGA or a GPU, these graphic processing units, because they're very powerful. Which should I use? And I don't know the answer. For the last few years, I've been saying I don't know. So really going to say there's advantages to both. And if we look at an FPGA, it's a reprogrammable. It's a very flexible architecture. You are only using what you need, so it's very efficient. And if you then, especially if you're prototyping and then looking to go into higher volume, you could very easily switch to an ASIC and build your high volume thing. GPUs though are also quite usable. They're perfectly suited for parallel processing, and as I point out here, there's a lot of parallel processing going on in a GNSS. I'll say a GNSS receiver or even signal generation. Either way, you've got multiple satellites. The constellations now are a couple dozen satellites each, even more. You got multiple frequencies. You've got multiple constellations. So there's a lot of things going on in parallel, and that's really what GPUs are designed for. And so GPUs, there's been a huge investment in GPUs, especially from the video gaming industry, so they're very powerful. And even though you think of graphics, but the kind of primitive functions of doing like convolution or multiply, add, multiply, shift, all those kinds of things that you do in image processing, we do a lot of those same things in signal processing. So there's a lot of commonality, a lot of efficiencies there by these powerful tools and that. And so parallelism, I would say, is probably the #1 thing. And in fact, for a little diagram, a little fun thing, if you want to see this, the picture I show here is a YouTube video from the Mythbusters. If you ever watch their things where they'll demonstrate things, and they demonstrated the power of parallel processing with the GPU by using a paintball gun system in which they took hundreds of parallel paintballs and within 180 milliseconds painted the Mona Lisa with a shooting of paintballs to show the concept, compared to if you were just trying to paint in a serial way with a serial system. So very powerful thing with GPUs. The other observation I guess I made about a year or two ago was also noticing when I'm seeing people using GPUs versus FPGAs is that GPUs seemed to me that they were advancing much faster in capability, the growth. As every time we go to use a new one, it's like, oh my God, there's so many more elements, so much more processing elements, and they actually could get obsolete pretty quick too. But so much thing there. So I found this from NVIDIA, which is a leader in GPUs. They make the bold claim, and I think this is maybe a little overstated, that Moore's law is dead now because GPUs are able to improve their performance much quicker than standard serial CPU, Fpga type processing. I wouldn't go that far to say it's dead, but I think, especially when you look at so much of the processing capability of CPU industry had been focused this last decade or two now, has been focused on the low power mobile application. So they did a lot of their innovation about reducing power consumption. The GPU people being used in video gaming and stuff is not as powerful, or that's not as a big driver. Although I think with some of the mobile things, we'll see more of it, but it's not a big driver. So something to consider too in your designs about power consumption. Those are the things there, but both work. So with that, I think they'll use that as a lead-in then for our next speakers. Lisa will be giving you the whole SDR approach from the signal generation side, and Zaid will be giving you the SDR open source approach from the reception side. And so with that, Mackenzie, I'll turn it back over to you.
Okay, great. So our next poll says, how do you plan to test your GNSS receiver? Will you use live sky testing, simulator testing, both live sky and simulator, or you don't know /other? Same as before, we will have 30 seconds to a minute to answer, so feel free to submit now.
Okay, good. And hopefully I didn't discourage anybody from saying, oh, you don't really need to use an SDR for your GNSS receiver, just use the off-the-shelf one. So it looks like I didn't scare people away with that bold statement. So people are still coming in here. Good, we're getting some good responses.
Okay, we have about 30 more seconds, so submit your answers now. Okay. Interesting.
Okay,
so they'll be using both.
Yeah, and if not that they would ask me, but if someone would ask me, I'd say yes. That would be the best way to do it, is to use both. There's power in both of them, and that's the best way to do it. So, well, great.
Okay, perfect. Now we will hand it over to Lisa.
Great. Thanks, John, and thanks, Mackenzie. So as John said, we're going to talk about the signal generation part, or the PNT simulation. So using software-defined architecture for PNT simulation. So just to jump right into the topic, we'll look here at the GNSS simulation approaches. So on the left, we have the fixed allocated hardware. And to frame it right, for an example of this, if you're familiar, is our Aurolia GSG56. So that is fixed allocated hardware. So that's the traditional GNSS simulation approach. The hardware for it was designed specifically for that product, for that software, and for that GNSS simulation purpose. It does use Fpgas. So as John said, Fpgas and GPUs are both perfectly valid approaches, and it's still true here. But there are some differences in the parallel processing power that make GPUs more suitable for our application. There's also could be some difficulty scaling to larger systems. So when I say a GSG6, it has its maximum channel count or signal count capability of 64. If I want more than that, really in that product, I need to buy a second unit, right? Whole full second unit, and then synchronize those together. So it's I have to double what I have in order to scale up. But when we look at the open software-defined architecture, this is what we're moving to, and what we've done with our Skydell simulator. It really allows us to have the maximum scalability and flexibility. We're not limited in any way by a hardware design. So if we want to do something new, we can, it's also in software. So we just need to locate which hardware is right for our approach, and we can adopt that. We can generate hundreds of signals in the GPU. And this is another one we're going to talk a lot about in the next few slides, but one way here with the software-defined architecture, I need more signals than the GPU I currently have. I can add another GPU to the system and have more capability for more signals. I don't need to buy a second whole unit. I could just buy the component, upgrade the component that I'm interested in upgrading or adding to. And of course, we have the benefit, like John said, of all the research and development and mass production of those GPUs, so we could take advantage of that. And we also, with using a purely software-defined architecture, we can have capability to support open source contributions without actually sharing our entire source code as open source. So in this part of the presentation, I will talk about scaling, how to scale up or down using software-defined architecture. Focus a little bit more on the GPU, talk about the data flow or how the data moves through the system, look at the latency. So we'll look at specifically the Skydell engine latency and the real-time performance graph so you can actually see what's going on in the system. And looking at the RF path, and so this is after we generate the RF, what kind of flexibility there that we have on configuration by using commercial off-the-shelf components that we can configure in different ways. So jumping to the data flow, this is really a basic system. I'm using Skydell, of course, as the example because that's what we're mostly familiar with. But in general, we can say that there's an engine there, a software engine that's going to compute all the raw information, and it's going to send that over to the GPU. The GPU is what's going to perform the modulation. So that happens in the baseband. We call that IQ data, and at that point, it's digital data. We send that over to the software-defined radio, which is what John was discussing, the architecture of that in the last section. And so that software-defined radio will convert that digital signal into an analog signal and actually at the right RF frequency that we program it to do. So in that way, this is how the data moves through the system, starting with the generation all the way to the computation to the generation of the signal. When we look at scaling, though, if I wanted to add more outputs, right? So I have the engine that's doing all the calculations. I have a GPU that's capable of doing all the processing I need, but I just need more outputs. So in this case, I could add multiple radios. So I can just expand that part of the system. I don't have to duplicate the other parts of the system, just the part that I'm interested in. So reasons why we would do this, one example would be to use multiple antennas in an anechoic chamber. So then, of course, we can have one software doing all the computations, one GPU doing the modulation, and send it to multiple radios to have multiple outputs in different parts of the anechoic chamber. Another use case is kind of what we show here, using 2 radios for GNSS. So we have 2 dedicated to GNSS, one doing L1 band, one doing L2 band, and then use the other 2 for jammers. So one jamming in the L1 band, one jamming in the L2 band. But again, we are able to scale just the part of the system that we need to grow. We're also able to, again, grow part of the system if we need to do more simulations. So we call this instances. In this case, instances of Skydell, and it really is just on a single computer or even over multiple computers. You have multiple copies of the software running. And we do this so that you can have different simulations, like within one box, you can have 2 vehicles being simulated, for example. And we'll set up one vehicle in instance 1 and one vehicle in instance 2. But that doesn't mean we also need to add a second GPU. If the GPU that we have is already sufficient to do the processing that we need, then we don't need to add it. We can use the same GPU for 2 Skydell instances, for example, and then send it to multiple software-defined radios. But in the case where you start adding things and the GPU does become a bottleneck in the system, we can actually rebalance that by adding another GPU. We can have multiple GPUs in the system. So instead of, again, buying another box and adding it, I could just add another GPU into the system and process the data from Skydell instance 1 with one GPU and Skydell instance 2 with the other GPU, and then again send those out to the radios. So it's kind of a different way to scale when we're looking at things, in individual components of a system rather than a system as a whole. we talked a lot about GPUs. John introduced the GPUs. I said it's what we use for processing. And as you know from my last few slides, I didn't give you a directed number on how many signals we can generate out of a GPU. That's because it becomes a little bit tricky. There's lots of variables in that. But the key thing here is that our architecture is not defined by the number of channels. It's defined by the compute capability of the GPU. So what is that compute capability? How do you know if a GPU is suitable for your application? Within Skydell, we have a built-in GPU benchmark tool that will help us do this. So we can say that when we have that open, when you're looking at GPU 0, all of these software-defined radios are set up to take signals from GPU 0. And we say, okay, these are the signals that we have selected, so multi-frequency signals. And then how many satellites do we have that we think are going to be in view? And this is all overall just a guess. Are you doing just GPS and GLONASS? Then you don't really care if you can how many Galileo satellites you can also generate, because it's not interesting to you. So you can set the number of satellites that you want, and then ultimately it's going to give you a score. And it's going to let you know whether this GPU can perform real-time simulation. By real-time simulation, we just mean that it has enough power, enough processing capability in order to generate our signals in time to deliver them to the radio, so the radio doesn't have an underrun. So we just need to make sure that we're getting the data to the radio, that we have the time to process it and get it to the radio in a consistent manner, every 1 millisecond for us, that is. So as long as the score is greater than 1, we can do it. If it's getting kind of close to 1, then you know you're on the border of what you can do. So you may want to start to think about adding a GPU or increasing the capability of the GPU that you have. But if you're well over 1, like this is 2.3, then you know that this system, as you have it set up here, is going to run fine. I'm talking a little bit more about the GPU selection, just to be clear about that. This is really specific to Skydell, but just a couple slides here where say that only NVIDIA GPUs are supported. So NVIDIA utilizes the NVIDIA CUDA cores, uses the CUDA programming language, so we are stuck to the NVIDIA for right now. But NVIDIA has 2 current architectures. They call them the Turing and the Ampere architectures. So depending on that architecture, depends on how you can evaluate that GPU to work with Skydell. So we say that on the bottom here, I said the basic rule of thumb is 16 CUDA cores per signal. When you look at something with the Turing architecture, we can use the number of NVIDIA published cores and divide that by 16 and get our, how many signals approximately that we would be able to generate with that GPU. But in the Ampere architecture, they redid the architecture a little bit, and that the way that they count CUDA cores and the type of processing units changed a little bit. So they, in order to estimate how much power you can get or how many signals you can generate on an Ampere architecture, you would divide it by the number of NVIDIA published CUDA cores by 2 first, and then apply the 16 CUDA core rule. So it's just a different ways to look at it. We have a complete guide for this published on our website on how to select a GPU for your use case. This is just, I just threw this in here so that as a reference material. There's so many NVIDIA GPUs, like John said, there's just so many. But here's like a chart just to kind of explain what I was saying. Like in the GSG 8 hardware platform that we provide, the RTX 85000 is what we use. So we consider the 4096 CUDA cores for Skydell. So going back to this image that we had seen at first, now we're just going to talk about it a little differently. So we said the raw data is computed by Skydell, so we call that the constellation worker. So it's computing all the data that we need to generate and set up the constellation. Then we send it over to the GPU. The IQ data is generated, and the computation is done in the GPU. And the modulation, that's where the modulation is done, so we call that one the modulation worker. And then the IQ data, of course, transmitted by the SDR, so we call that the streamer worker, because we're actually streaming data really from the GPU to the SDR, and it needs to be there reliably. So when we take that and we replace those with those pieces of it with those worker, then we can start to look at what type of processing is happening in different parts of the system. So for us, Skydell runs at 1000 hertz update rate, so everything we do is in 1 millisecond chunks. So we say like a chunk of data that we need to send through the system, every chunk of data is 1 millisecond. We say that if we have the 1 millisecond chunk, it has to go through all 3 of the workers, obviously, to get to the end, so where we can make RS. And by doing that, we're saying we're putting it through the pipeline, right? This is the pipeline from constellation worker to modulation worker to streamer worker. Now we say we have that in the previous one, it was just one set of them, but we're trying to generate a bunch of data and make sure that we have a 1 millisecond chunk available every millisecond. And it's not always possible to, for each of these workers to do their part within less than 1 millisecond in order to have it. So we need to do things in parallel, and that's where we take advantage of that parallel processing capability of the GPU. We're able to be generating these 1 millisecond chunks in advance, and it's happening in parallel. So we're generating multiples so that it's ready to go when the radio needs that. In order for us to do that, how it flows through the system is we timestamp everything. So we know when the constellation worker started and when it ended. We know when the modulation worker started, when it ended, when the streamer worker and when it ended, and then when it's time to transmit. So you can see here in the drawing that there's variable amount of time that each worker could take, but at the end there needs to be a 1 millisecond chunk available, and that is not variable, right? We don't have any variability there, so we have to have the data ready in advance. Here's an example of where the workers might be falling behind and causing an underrun. So in a system that's kind of reaching its level of maximum capability, you might sometimes see this, or if you try to do something else on the system, so you try to use whatever computer you're using, you try to do something else, even something like opening a web browser, it takes away from the processing of the PC, and it could impact the timing here. So we want to keep an eye on it and make sure that we are able to generate everything before we need it. Otherwise, we run into this underrun scenario where we don't have anything to transmit. And as you know, GPS needs a continuous signal. We can't have that interruption, especially when we're doing the GNSS simulation. So we are able to configure the system latency. So here I'm going to show you the screenshot where we can set the engine latency. I put here 50 milliseconds, but what this really means is it's the maximum amount of time that will allow the real-time engine to generate those chunks in advance. So it's especially applicable for hardware in the loop. So how much in advance how much latency can you take in the system? For regular generation, you can leave it at a higher level so that it can accommodate if there's any something is getting close to underrunning. Might be, if you have the latency and have it process it even further in the past, then it might be able to keep up. So that's how we do that setting there. And on the top, you can see the Skydell performance graph. So all these little, the workers are shown here, like how much time did the constellation worker take, how much time did the modulator take, and how much time did the streamer take. You can see that in the graph. So you should see that for the last minute. So you see in this graph that we're really not close to reaching the limit there. So everything's performing well. It's nice and steady in that image. And then you also have on the right the last second. So if you're trying to investigate, okay, I had something happen here, I had an underrun, I don't understand why, you can kind of dig in to that last second and see, because remember, we're doing this 1,000 times per second. So even though 1 second of graph data doesn't seem like a lot, it really is still 1,000 data points in that 1 second. And just to flow then from how the data flows and how the Skydell is able to vary the latency and get low latency and optimizations, we'll move into now it being hardware independent. So again, everything I'm talking about here in the previous slides is all done in the software, right? So there's no dependency on the hardware there. And we can use different types of hardware, different radios, different GPUs, different PCs, different operating systems. All of those things can be variable. For example, the SDR block could be something that's inside the PC with the GPU and running the Skydell software, running our simulation software, or it could be something that's in our where the simulation software and the GPU are together in the PC, but the software-defined radios are outside of that PC. So both architectures are fine. It just depends on which, what the setup is like, what you might have access to. These NI Edis research radios are very widely used in academics and research facilities, so you might already have those. You take advantage of those. If you're putting together a new system, you might rather put everything in the box and use a PCIe-based radio, and that's an option as well. So we support multiple radios in order to allow maximum flexibility and configurability for your system. And we also have that same approach to the RF connections. So on the back of, this is like consider this like our GSG-8 product, but it really could be any PC. You can put the radios, into the PC, and we're able to do all of the attenuation, DC blocking on the output of it. So this is just a very straightforward. One radio, it's being attenuated, so the radios themselves, because there are commercial off-the-shelf equipment, not purpose-designed, the range of power is generally higher. Because GNSS works at such a low power level, the range is higher for the, sorry, I lost that. But okay, let me just move on. That we're going to output at minus 80 dBm typically from the SDR. So we need to attenuate that. If we attenuate that by 30, we get a minus 110, which we know is a good signal coming from like a low noise amplifier. But we can also then say, now I want to add another radio and I want to use that second radio for jamming. So I don't want to attenuate both of those signals by the same amount. I want to move that attenuator only onto one of the lines. So I can move that attenuator before this combiner. And when I do that, now I have 30 dB additional attenuation on the GNSS signal, but the jamming signal can be already 30 dB higher without any software control. And it makes it a lot easier for us to set up those higher J to S ratio scenarios. And then we can even do it where we use, basically 2 simulators in one box, right? You have 4 radios here. 2 of them are going to one receiver. 2 of them are going to the other receiver. And we're actually running 2 separate simulations using, we've used 2 separate instances of Skydell, maybe for 2 different vehicles. And then to wrap that up, just the benefits of the software-defined architecture that we looked at is that it's decoupled from the hardware. The hardware is defined by the software, so the software-defined radio is not dedicated to anything specific, like not to GNSS or jamming or spoofing. We can use it as we need to. We can share the GPU capability, and we can also generate a lot of signals and expand the system and do upgrades to the system without requiring a complete replacement of the system or a complete additional system. And then I will throw it back over to you, Mackenzie. I think we're having another poll.
Yep, okay, so this last poll, why are you using / considering to use a GNSS SDR? Is it for cost savings, if you need custom performance features, another reason, or you're not going to use it? You can go ahead and submit your answers now.
I think we anticipate, based on the answer to the first question we asked, I think we had about 2/3 of our audience was saying that they were at least using or considering to use this. So it would be nice to know why.
We will do about 30 more seconds on this slide. Okay. Interesting.
Okay,
All right.
great. Yeah. Yeah, they need custom performance, which I would say is a good reason. But I guess almost a third have another reason, which we didn't anticipate. So we can maybe keep the dialogue going. Some of you that answered that other reason, please have a dialogue with us, and maybe we can help you.
All right, and now we will hand it over to Zahid.
Hello, everybody. Thank you, Mackenzie. So I'll be talking about our software receiver, Fpga open source multi-Gnss software receiver that we recently released as open source. So I have actually quite many slides today, but I will try to skip some slides because I think we do not have much time. Seems like there's not much time. So in the first section, I will give some background information about Fpga, and then about the architecture and some features of the Fpga software-defined receiver. And then in the next section, I think it will be quite interesting. I will try to highlight some research results that we obtained in the last 1 decade while we are developing the receiver. So what kind of research cases, and now from the poll you have seen that there is these custom cases that can really be used in Gnss SDRs. So I try to give some overview of what we have done in our institute. And then there is this interesting case I have where in the last section you'll see some demonstration of a spoofing attack. In that case, I used some data from University of Texas and try to show to the audience that what actually happens inside the tracking loop and how the spoofer actually take away the authenticated signal. Okay, so the software receiver, it is a multi-Gnss software receiver. We have our own version of the software receiver that is a multi-frequency multi-Gnss software receiver. The one that we released is a multi-Gnss software receiver with GPS, Galileo, Boidu, Gnss, and Navic capability. But the one that we have in our lab, it has much more capabilities. So I will try to basically tell from that perspective in general. So as you could see that it is basically offering quite a lot of interesting features that has been discussed before as well in the presentation. And I will most likely give some results in later on as well. In general, if we think of this kind of architecture, so what it does is basically it takes input from the user, a parameter file. Basically, the user can configure each block quite flexibly. Basically, if someone would like to just try out the performance of acquisition block, so he or she can do that quite nicely, and then they just need to change the parameters in the acquisition block. And in the same way, if someone would like to change some parameters in the tracking block, he or she can also do that. And also how we have developed it over the years is so that we save data in between. So ideally you can see here the red stories. It means that the user can save at any certain point the data and then basically load it afterwards for their own need. So there are options for that, and the software actually checks if the IQ data are already processed or not. And if it is already processed, then there is this track data or acquisition data available. So it basically starts working afterwards. So in that way, it gives a lot of flexibility to the end user, considering the fact that usually the tracking takes quite a lot of time because it has to do correlation with multiple signals and multiple channels. So it is usually a bit time consuming to go through. But and then also one other interesting fact is that if someone would like to, for example, try to compare the performance of different atmospheric models, for example, how curvature works, what is the accuracy someone would get at a certain latitude, and would like to compare it with the precise product that someone can get from IGS as IONX files, so that you can do also pretty flexibly in this kind of architecture. Okay, so here is some kind of backgrounds about the software receiver. So we started working in 2012 on the first version of the book that Professor Kaibore and his his colleagues were released in end of 2006 or beginning of 2007 with the book. And we started working from there and made some customization with Galileo satellites, GeoPay and GeoP satellites. And then eventually we made it capable with Galileo tracking and decoding the Galileo navigation message. And then in 2013, we managed to get a Galileo-only position fix with 4 RV satellites at that time. And then in 2014, we were able to make this Boidu receiver implementation. And from Finland, we could see at that time about 5 to 7 satellites, Finland being in the kind of little bit eastern side in Finland. In Europe, so we were able to see some good number of satellites, Boidu satellites at that time. And then we move on, and we also started to think of implementing NAVIC, or at that time it was called the IRNSS satellite system, which is a regional system, and we were able to see about 2 to 3 satellites at that time point. And we kind of implemented NAVIC, and then we had some results with that. And then in 2017, we started working with this second version of the book, which is called Gnss Software Receivers, with Professor Kaibore and with other editors, Ignacio Fernandez, and Jose Lopez Alocado and myself, and the whole unit at FGI and some other authors. And finally, we were able to finish the book in 2021, and now it is in press with Cambridge University, and should come out in sometime in end of this year. Okay, so how my screen is pleased. Can anyone? For some reason, the screen is not moving for me. Can anyone change the slide?
Yeah. I think we've gone on to your next slide here. So we now have slide 6 of 51 is showing.
Yeah, I will refresh my bit. So let's see if it works. There is seems to be something. Okay, so yeah, I think I am seeing slide number 51 now. Okay, so let me just...
6, yeah, 6,
so
651, that's okay. 5.
Yes.
Yeah.
Yeah.
Okay, you got it.
So this is giving some list of signals that you could, with a software receiver, you could actually process. And we have all these features in it. And maybe I can skip this slide. And this is a very typical software receiver architecture. And John has already kind of given an overview of the architecture from front-end point of view. And from here, you could see that we really need some kind of front-end. Usually, we use one from Teleorbit, or it can be also directly from Aurelia simulator, which can give you this kind of IQ sample files. Depending on what kind of constellation you'd like and what kind of user need you have, you can make your constellation, and you save the data file here. And then this block diagram is pretty standard for any GNSS receiver. And if it is a GNSS software-defined receiver, it's quite standard. Okay. The FPGA software receiver is a kind of research tool, and it's not a production ready. So we will not guarantee that it will work in all situations. So this is just a disclaimer. And as I was mentioning about the parameters, so we use some block of parameters. So some parameters are system parameters, some parameters are navigation parameters, some are tracking parameters, and some are acquisition parameters. So they are kind of made it so that the user could really understand it in a very nice way. And again, we kind of group them in a way, in a signal-specific way, because there are some changes in the signals. For example, the code frequencies will be changing from L1 to L5, from Galileo E1 to E5A. And some signals have NH coordinate, secondary codes, and some have data channel and pilot channel. So in this way, we kind of differentiate from one signal to other and one frequency to other frequency. And the way it works is it's not fully optimized from a running point of view. So it has this kind of sequential nature of how it processes one file to the other. But this is again also quite generic in nature. So here you see some example of acquisition configuration. So this is kind of by default it is defined there, but the user would like to can change it depending on what he or she is interested in, and basically play around with the software. So this is just one example case where you could see here that if for Galileo E1 signal, if you use data and pilot, you would see some signal and energy boost hubs, because there are two pilot components in there, and you can use either coherent or non-coherent combination of data and pilot channels, and that will help you with acquisition statistics. Yeah, so I think I'm going to skip that as well. For in regard to tracking, we use this kind of table-based tracking, and it is so that we make the tracking depending on the code length. So for example, for GPS L1, it is a 1 millisecond code repetition. So we call the tracking block after each 1 millisecond, but for example, for Galileo E1, it's about 4 milliseconds. So for the tracking table, you can see that it is designed in such a way that user could design the tracking parameters depending on the signals. So it uses a tracking table. If I go on to the next slide, you see that there is this kind of tracking table where it has all the functions that it needs for tracking. For example, frequency lock loop, phase lock loop, and other functions if you need to compute signal power and the code discrimination, code loop filter, and all these details are mentioned here. And if you would like to test, for example, a couple of different kind of signal power estimator, so you have possibilities to actually, in this case, you have seen that there are two estimators that we use in this particular case. And again, for tracking, this is also quite standard that we start with a hold acquisition, and then it kind of the tracking takes the acquisition parameters and kind of initiate it as a state pulling mode, and then we kind of close in the loop and move to coarse tracking, and then finally we move to fine tracking when we have much more confidence on the signal to power noise ratio, and then also the loop clock indicator giving us good value. So here is a typical example of the tracking channel. I think this is what we usually see in case when it is working quite nicely. And one other interesting feature is this multicultural tracking. So meaning that the user could actually choose one specific channel. It can be one or it can be all the channels depending on how he defined this parameter. And then the user could also select that what would be the update rate. So if it would be only called after 50 milliseconds or 100 milliseconds or whatever, one second or so. The reason of such choice is that it takes quite a lot of time for doing correlation. So the user can kind of decide depending on his or her need. They can kind of choose on. Yeah. So I think I can keep here as well. So this is one example correlation output. In this case, we used 17 correlators. Here you see that it's a typical GPS L1 correlation shape. And this is one example case how you can utilize this kind of multi-correlator values. So we implemented some parameter called channel quality index, which basically computes the area of this triangular shape function. And with this kind of this is a standard equation to compute the area of the polygon. And we use it to know that how much the signal is affected by multipath, for example. And here we have this one example case where you could see that some of the satellites we intentionally added multipath with this Skydell simulator. And in this case, you could see that the satellites with multipath, they were not really giving, or they are not really close to 1, which should be for GPSL1 BPSK signal, it should be close to 1. But it is not, just because of multipath. And this is how it basically looks like here, as you could see. So yeah, so now what we did in the paper is basically we put the CQI on, and we see that if it is outside the boundary, so we basically reject the satellites and basically compute the position only with those satellites which are within the boundary. Okay. I think I'm going to skip this slide as well, and this is quite straightforward how you can enable a signal. So you basically need to change, just add on the signal, and then basically define the parameters within the signal. And some parameters are already known, so the user does not need to kind of input those parameters, but they are in the get system parameters function, where all the specific constant parameters are defined. And then we try to reuse the codes as much as possible. For example, the tracking groups, if they are the same, if they do not change from one signal to the other, we actually use the same kind of functions in a very nice way. But then some functions must have to change. For example, we are generating the parent codes, and some has GPSK modulation, and some has BOC modulation. So for that, we have to change the functions, and we did that with the naming here. Yes, and then this is again pretty standard for how we decode the ephemeris function. So I'll skip this slide. And then for ionosphere and troposphere, we have all these models. The user just need to mention what signal it is, and if it is a Klobuchar or Galileo U1, it automatically switch to Nyquist model. If it is a Galileo U1 and it's a Klobuchar one, then it's for GPSL1 and V2B1. And as I mentioned earlier, the user could actually select if it is if they have IONX file, so they can also put that IONX file in the text file, and then they can get some performance improvement. We have also for these troposphere corrections with subsamoan and zenith hydrostatic delay model, and but the user could actually define use another kind of model if they would like, and it's just a matter of adding functions there. Okay, I think I have not had much time left, so I will try to give some quick overview of what is possible here. So with GNSS modernization, we know that the new modernized signals have higher code length and higher code rate. So that basically means that you would have possibilities to improve your signal quality with greater complexity, for example. So if someone would like to implement alt-box, so they need to use the high bandwidth signal from E5A and E5B, and basically get this kind of performance improvement. As you could see that if they would use only one signal component, so it basically improves 3 dB. But if all 4 components are being used, then the user should be able to see about 6 dB. And we have had this publication published last year, or in 2020, where you can see the details. Okay, so here again some demonstration of the same publication, and here you can see that we use a very wideband jammer on L5 by full band, and you'll be able to see that the alt-box one sustains much better than the other signals. Okay, so we tried out different options to implement also adaptive notch filter. So basically looking at the frequency domain and basically applying knowing the bandwidth and where it is exactly at the frequency domain, and then convert it back to the time domain and apply the notch filter. So you can see the publication here, which is published in 2018. Okay, I think I'm going to skip that. So this is just to tell that this CN0 estimators, there are different versions of CN0 estimators, and the one that is used in, before is basically this. They have kind of different variations, and especially with a new signal. Ideally, the one you can see from here that, for example, for Boidu, they have NH code, and the traditional narrowband power-based technique might not work properly. So that can be seen from here, that with low SNR values, it has kind of deviation gap here. Okay, I think I can jump quickly. And again, this is some tool that you can use if you have a Gnss SDR kind of receiver. So you can use the distribution of IQ in a way that it will detect if there is any imbalance due to jamming or spoofing, and you right away see that there is something happening if you do a chi-square test on IQ Gnss, for example. Again, this is a concept illustration of a resilient multi-frequency, multi-constellation receiver. What we did here is we checked that if any of the frequencies are being interrupted by jamming, L1 only jamming or L5 only jamming, then we switch to other bands. And in case of jamming on both the bands, then we try to survive with all the frequencies that it has. And we kind of show that it works quite nicely with this kind of approach. Okay, so I'm kind of quite close to my. So here I have. Okay, so it's not working for me. Okay, so now it's working. So here you can see in the text stack file. So this is a scenario 4, and what you are seeing here is this blue one is the estimated correlation peak. Well, we have 41 correlator points here. And the spoofer is already kind of attacked, and you can see that how it is kind of being deviated, and now it is taking away. So the authentic signal should be here in the 0th prompt delay, but here you see that there is an offset of about minus 1.4 chips, which gives us a pseudo-range error of about 470 meters. And this is what happens with one advanced algorithm that we developed earlier, which is called a reduced search space maximum likelihood delay estimator. And in this case, you cannot see any correlation peak because we use a spoofing detector. And once we detect a spoofing, only then we apply this multi-correlation because it is quite expensive to kind of do the correlation. And here you see that the peak is the reduced search space maximum likelihood estimator is basically nicely able to make the authentic peak around the prompt delay, and the spoofer was not fully able to take it away. It has some. So this is the authentic signal, and this is now the spoofing signal here. Okay, so this is. I think what happens usually if you have would like to see what happens for spoofing, and they would like to kind of sync together the spoof and the authentic signal. Okay, so this is the algorithm I was mentioning. So this is a version of multi-path estimating delay log loop, which we named as reduced search space maximum likelihood delay estimator. If you are interested, you can have a look in the paper here. Okay, I'll probably skip this slide. It's just so this is the ultimate result that we get with a new advanced algorithm with 41 correlators. It's not the optimum, but at least you get some improvement with we run it for about 300 seconds, and you see some improvement here. Okay, so this is here you get all the details about the JGFRX and who contributed from FGI about the software receiver. And I'll be happy to answer your questions if you have any. Thank you.
Okay, great. All right, we are now going to transition into Q&A. So our first question is, how does availability of too many satellites, how is that advantageous for PNT?
Okay, I guess I could cover that one. This is John. I would say, yeah, you can never have too many satellites. Almost you get redundant information, and in fact, the what's sometimes called the RAIM function or receiver autonomous integrity monitoring uses that fact that you have an overdetermined problem, you've got redundant information to maybe sort out problems and eliminate maybe a bad satellite or some bad things there. So, yeah, it's a real advantage for that reason.
Okay, and then we have time for one more question. What are the key advantages or motivations for utilizing GNSS software-defined receivers?
Yes, I can take that. Yeah. So I think John has already mentioned the real advantages of using a software-defined receiver. So ideally, as we see from different applications point of view, the needs are different. For road, there is one set of requirements, and for aviation, it's a different set of requirements. So if someone would like to kind of develop the algorithm, innovative algorithm, I think it's better to switch to something that where the developer has full control over it, and in that way they can save the hardware development cycle. So ideally, anybody could make their own custom receiver depending on the user needs.
Okay, perfect.
Great.
Thank you all.
Mackenzie, I saw that there's a number of questions that came in real time. We can get back to the folks individually on those. So thank you for those questions too. We'll get back to you folks.
Okay, perfect. All right. Thank you all for attending today's webinar, Exploring Advancements in Open Source Defined Architecture for PNT, brought to you by GPS World Magazine and our sponsor of the event, Aurelia. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you will see on this slide. The resources panel does house a PDF of today's presentation slides, which are available for you to download. To access this panel, you can click the green icon at the far right end of the toolbar at the bottom of your screen. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be available and posted to this page. As John said, they will be reaching out to you regarding any questions, but again, feel free to reach out using their email addresses. Thank you all for attending, and we hope you'll join us again soon for another great webinar.